a bit later. I just printed it, so it's going to be quicker for you to follow without having to write down. Goodness, there's a little story that comes with it. I didn't lose my voice watching the Super Bowl. I don't know why. You guys watched it? Enjoyed it? It seems like it. I watched the beginning a little bit. I'm a Vikings fan, so I didn't want to watch any of that thing anymore.
Hello.
And yeah, if you ask me why do I root for the Vikings, because there was no NFL team when I was a kid in Canada. So, and I thought the helmet was pretty cool. So I'm a true fan because I'm sticking with them, even though they suck for a long time. So, let's see.
You could be a Dolphins fan.
Yeah, that's worse. Huh? I remember actually when I moved to Florida, we visited a friend in Miami, and they were watching, I think it was a playoff game against the Jets and the Dolphins, and I realized that it was a bad thing to be a Jets fan that time. They were so mad. Oh my goodness, that they lost. Okay, so let's see. Not football. Oh, look at this. So, last time we started talking a little bit more in detail about vibration and establishing a few basic concepts. We don't have to rewrite this, okay? But we established that the movement of our mass on the cushion or spring could be represented by this function, okay? We say that P was the angular or circular frequency equals to 2 pi times the actual frequency of the vibration. T is the time, this was the amplitude, okay? So we talked about this, we got a little schematic that established this, then we jump back to springs, and we establish a few concepts. We talked about, from this, that's important. What we looked at is that if we took that derivative twice, it gives us the acceleration as a function of time, and we established that the maximum acceleration, okay, is AP squared, or A times 2 pi f squared, like this. So, and that's one thing, let me tell you this, we don't have to memorize a lot of things, okay, in this class, and actually all these equations you may not remember. I'll provide you an equation sheet, you'll have all of this. But you need to know that we use little a for acceleration, okay, and big A is the amplitude, okay? If you ask me at the exam, what is A, I'm not going to tell you, okay? You need to know these things, okay, because we're going to use that so many times, okay? So, and again, here, this is kind of actually the real way to write this down, that this will also be max in a way, so that's the amplitude, but it's the amplitude get down. No way the amplitude is this guy. But everything we're going to look at is maximum, okay? Because we want to look at what would be, when he vibrates, what would be the maximum vibration or condition associated with this. So then we looked at one more thing. We established a static deflection. Okay, we mentioned that if you set a mass, okay, on a spring, it's going to deflect it by a certain amount because of its weight. Okay, and we established that deflection as the static deflection. That will be its weight divided by the spring constant. So this is what we've done, and then we talked a little bit about cushions in series and in parallel, okay? And we established relations that might come handy a little bit later. Oh, we did a lot more than I remember, okay? We did this, and finally what we did, we talked about the modulus of elasticity. We mentioned that the modulus of elasticity, E, was the ratio of the stress, okay, over strain. Okay, we define these terms, and then we mentioned that the stress was the force over a certain area, and the strain was a certain deformation over an initial thickness. We reorganized this, and we found out that we could actually calculate the spring constant of one of these cushions using that equation right here. So the thing about this is that whatever shape of a cushion it is, okay, it can be very large area and thin, or shorter area and thicker. If it's the same material, they will have the same modulus of elasticity here, okay? But they will have different stiffness, okay, if you want, or spring constant, because if you apply the force on a large area, okay, you're going to have less deflection than if it's a smaller area, okay? So, that's pretty straightforward, but that's what we established. We did a little example on this, okay, and that's how we ended the class. So if you guys missed last lecture, make sure you get the notes from one of your colleagues, okay? Once you revise those notes, okay, if you do have questions, don't hesitate to come and see me. I'll help you out, but make sure you have the notes and show me that you've done some of your homework to make sure you can catch up to what we've done so far. Okay, so next step, we're going to establish a few important concepts. Okay, we're going to talk a bit more about free vibration, okay, and more particularly about natural frequency. Okay, natural frequency, we're going to write down as F sub n, okay, and this as units of 1 over second or hertz, okay? And again, this, as you will see a little bit later, this is first step, okay, to get into what we are really after, which are forced vibration, okay? But we need to know the natural frequency, we need to know where it comes from and what it is, and we'll realize a little bit later that the natural frequency of our system, and I always say system because it has to be typically like a mass and spring system, okay, will be a characteristic of our system, and that will be very important to find out what will be the response, okay, we'll get when we expose our system to a force vibration, because that's what happens. So free vibration, that's the classic example, again, of like a pendulum that you set into motion and it's vibrating freely. The idea, it is idealized, but is that the vibration would go on forever and ever. Okay, it's not going to happen, but that's the main assumption for free vibration. Same thing with if you pluck a guitar string, it's going to vibrate at its natural frequency and give out a note, okay? So a lot of these vibrations, they're real life, they're dampened. We're going to talk about it later, okay? At this point, we assume that when we set the system in motion, it's going to vibrate forever and ever, okay? And that's what's called free vibration, and now we'll see that in that case, the system vibrates at its natural frequency. Only in that case, if it's freely vibrating, okay? What we'll look at next is what if we impose a motion that creates a vibration, okay? So it's not going to vibrate at its natural frequency anymore, but the natural frequency will play a role to find out how it will vibrate. So let's start here with a little bit of an analysis here. So what we'll have, okay? I should write down a little sentence here to write down, introduce what we'll do. So assume that a force is momentarily applied to ideal spring mass system. System is then set in motion. And here we're going to put in parentheses free vibration. We want to analyze that motion. Okay. So let's see here what we'll have. I'm going to go here so that you have space to start to write this down. So we have our mass that sets into a spring like this. Okay. I'm going to have two drawing in parallel here, if you don't mind. We have the mass, and we have the force of the spring that's going to act up on our body here.
Is x equals 0 always at the bottom of the weight? Or?
It doesn't matter. You can put it here as long as it's a reference. Okay. And we're going to apply here, or just define here, the static deflection as follows. Okay. So initially, it's obviously exaggerated the displacement here, just to make sure that we see it nicely. But the mass, the spring is set here initially. Put the mass on because of its weight. It went back down. Okay. And to set it in motion, what we'll do is either you're going to stretch it, okay, or you're going to push on it with a certain distance, and you're going to release it. It's going to be oscillating. Okay. So now what you have to think about here, just a few things. Okay. If you are at, let's see, if you are at x equals 0, what you have, okay, is that the force of the spring, okay, is equal to k times the static deflection, okay? And we know, by definition, okay, this is equal to the weight. So right there, the mass is there. There's no, as we will see, there's no acceleration, okay? Because the only two forces that act on our system are going to be able to balance themselves. If x is equal to the static deflection, okay, that means here that the force of the spring is going to be equal to 0, okay, and that means the only force that's going to be going down is going to be the weight, okay, just to give us an idea of what's going on here. So to analyze our system, what we're going to have to do is we're going to look at the sum of the force in the x direction, and we know that this is going to be equal to the mass, okay, times the acceleration in the x direction, F equal mma, okay. And then here, okay, our acceleration is d squared x dt squared. So based on this, okay, the two forces we have, okay, is the first is the force of the spring. The force of the spring is using Hooke's law, so it's minus k times the displacement. So the displacement is going to be x, okay? But you need to take into account the static deflection, okay? Because that spring initially is already compressed by a certain amount, okay? So that's very important that we take that into account.
Okay, so why is that x is equal to the little squiggle st? The force of the spring is equal to 0.
What? Here?
The second one, that one, yeah. I don't understand why f of s is 0.
I'll show you, okay? We're getting there, okay? So this will be minus the weight. All of this equals to the mass time acceleration, d squared x. Maybe I should have written this first. dt squared. So if we look at this now, this might illustrate these two things a little bit better. But obviously, you know that if there's no mass here, okay, the spring is going to set right there, okay? So we know that if x, okay, goes back to the static deflection here, okay, that means the force of the spring has to be 0, okay? It's at its equilibrium position. The spring is not compressed and it's not stretched in any way. So when the spring is there, the force of the spring, which is this guy here, okay, has to be equal to 0. That's why we need to correct and take into account that guy here, okay? So in a way, that also means here that our acceleration is going to be 0. If x is equal to the static deflection right here, okay? That's what, oh no. If x is equal to the static deflection here, this goes to 0, okay? That means that we have a negative acceleration right here. That means that the force, the weight, is going to try to pull it back down, which makes sense, okay? So, again, just think about this, okay? Go back into this, make sure that you understand that. So that is our first step here. Now, obviously, we need to remember a few things, okay? The static deflection is the weight over the spring constant, and the weight, obviously, is the mass times the gravitational acceleration. So we can expand this a little bit, okay? We're going to have minus kx plus k times the static deflection minus w equals m d squared x dt squared. Now, if we realize what the static deflection is, and we use this, the weight over k minus w, things are going to start to simplify a little bit. So you see those 2k here simplify, and we have plus the weight minus the weight. So these will also simplify, and we end up with minus kx equals m d squared x dt squared. So this is not a nice form of the equation. Let's rearrange that a little bit better. We can write d squared x dt squared equals, plus k over m times x equals 0. Should have time to catch up here a little bit. Some of you have done, I don't know how much you use still, solve differential equation and so on. Some of you don't like this at all, which is weird because you're engineers. But, okay, so this is an ordinary differential equation, okay, because we have a function, okay, of time only. It's second order because we have the second order derivative with respect to time. It has constant coefficient, and it's also homogeneous because it is equal to 0, and all of these terms include a function of the dependent variable x.
Is that like sine and cosine or sinh and cos?
It depends, yeah. Okay, but in this case, this solution can be taken as sine and cosine, but generally, when you start to tackle this function, okay, what you will do, okay, you will assume a solution of the form e to the lambda x like this, okay? Because in a way, this is something you need to look beyond the math and just think about this. This is, think about a function x, that when you derive it twice and you add the same function times a constant, it's equal to itself. So there's not a function that satisfies that case, okay? Exponential is 1, and as you guys probably remember that depending if the argument of the exponential is real or complex, okay, this can become as well sine or hyperbolic function, okay? So that means, okay, from there, dx dt is lambda e to the lambda x. It also means that d square x dt square, if you remember, is lambda square e lambda x, okay? So this becomes, if we replace those functions in here, lambda square e to the lambda x, okay, or lambda t, sorry. Guys are so nice, you didn't want to tell me I was wrong, okay. It's a t, okay. I teach another graduate level class, and the students are always like, oh, you made a mistake, you made a mistake. Man, I was like, how many mistakes do I make in my undergraduate class and no one tell me? So, anyways. So, all the t's are corrected here. Okay, so that'll be k over m e to the lambda t, okay, equals 0. Those exponential functions simplify nicely. Okay, then we end up here with lambda squared equals minus k over m. So, k and m, can they be negative? No, okay, k is a spring constant, has to be positive. The mass is going to be positive. Okay, so we end up here with a value, okay, it's going to be plus or minus I square root of k over m. Okay, I, you see, if you remember, square root of minus 1. So, what we do, okay, just because we don't want to carry this guy around too long, okay, we're going to assume, or we're going to write that P equals to K over M. So our general solution here, okay, because there's two solutions, that means the general solution of our equation is going to be a certain constant C1 times the first solution, I pt plus C2 e to minus I pt. So the thing is, exponential functions are really useful if you remember your calculus classes or differential equation classes. They're pretty useful if you're dealing with semi-infinite domain or something like this, when one of the variables goes to infinity. It simplifies very nicely, but it's not very convenient for a lot of other finite domain or an application like this. Particularly here, we're dealing with vibration. So, as one pointed out, we should want to try to get to sine and cosine, okay? Because that's typically how we described them before. So the thing now to realize, okay, I don't know if you remember these, but cosine of x, for example, let me keep on the t. So you can always express this as e to the it plus e to the minus it over 2, and the sine of t is e to the it minus e to the minus it over 2I. Okay, you can show that with Taylor series expansion in a bunch of different ways. Okay, so that means that, bless you, these are just linear combination of the solution. There's nothing that prevents us of taking those solutions and multiplying, adding them to different shape and size, okay, to create a different solution based on sine and cosine. So oftentimes, actually, you can just write these solutions directly from that differential equation, okay, to that form without any issue, okay? So we have with this, it's the same general solution. We include two of these solutions, and each of them are linearly independent. If you remember, if you divide one by the other, you're never going to get a constant, okay, which is essential. So with these, we get a little bit closer to the shape we want, cosine and sine, but it's still kind of a not very useful situation here. So we can retransform this even more, okay? So what we'll do, okay, we're going to make use of trigonometric identity and so on to try to reformat this into a nicer format. What we'll do is we will let C3, we're going to assume that C3 is equal to a certain constant A times cosine of a different angle. We'll find out that this is actually the phase angle, phi, and we're going to say that C4, okay, is A sine. What we're doing here, we're just expressing two constants, a function of two other constants. That will simplify our expression. So from there, you could show that A is going to be the square root of C3 squared plus C4 squared. And you can also find that B is the arctangent of C4 over C3. So if we replace that into our general solution here, okay, we obtain that x of t now. We're going to have a in both of these terms, so we can take it out here. I'm going to have cosine pt times cosine phi plus sine of pt sine phi. Like this. So this is a nicer form because we have a sum of cosine and a sum. Oh, I messed it up. Did I? I did mess it up. Sorry, guys. Okay, so I didn't look at my notes right. Okay, we should in here, please. I really apologize. Okay, I should watch my notes better. We need to have a sine here, and we need to have a cosine, and this will change here. I'm really sorry about that. So in here we change this, and in here we have to change this. I'm sorry. That should make more sense now. When you look at this, this is a trigonometric identity here. We can realize that sine of A plus B, if you remember, is sine A cos B plus sine B cosine A. So this equation now becomes just sine PT plus B. I apologize. I hate making mistakes. So, you remember some of your classes in physics as well. This is the shift or phase angle. Okay, what it does is just shift the vibration on the x-axis, okay, or the time axis. Okay, so for us, what we're trying to look at here, we have a vibration that's go on and on and on and on, and even in a packaging application, it's not a big deal where it started. Okay, what we are after is really the amplitude and maximum acceleration and so on. So for our purposes, okay, this is kind of arbitrary. Okay, so what we'll do, okay, so for our application, going to assume P will be equal to 0. Just even nicer. Okay? So all of this leads to our equation that we've seen before. Okay? But at least we have a rational step-by-step procedure to show its origin. Okay? So, from there, okay, we know that this argument here, okay, for t equals a period t, we know that pt equals 2 pi. That's how we have to define this function. Okay, that has to be figured out. So we actually found, okay, from there that obviously the period here is the inverse of the function of the frequency. So the frequency, and we find that we are after the frequency in this case. Okay, it's going to be 1 over 2 pi times p. And p, if you remember a little bit earlier, we defined this as k over m. So this would be the frequency at which our 3D vibrating system is going to be vibrating. By definition, this frequency f is the natural frequency of the spring mass system. So that's why we're going to always write this guy with a little n, okay? It'll be 1 over 2 pi square root of k over n.
Why does that frequency not go to 0?
Why would it go to 0?
Because you start it and then it should stop eventually, you know?
Yeah, but this is in the case if you're dealing with dampening. We are dealing with an ideal case where we assume
okay, so it's always
going to go. We're going to include dampening a little bit later. Okay, so and we're going to talk about that a little bit later. So that means, okay, at this point, that we have defined the frequency at which 3D vibrating systems are vibrating. It's depending on the stiffness of the cushion and the mass of our product. So that's why we're going to see it is really a characteristic of our system. Now, again, this is only, okay, this is only for free vibrating system. Meaning that these are the only systems that will vibrate at that natural frequency. Sometimes you can see a different form of this equation, okay? We can always transform it a little bit, okay? And how we do this is we multiply the top and bottom here by the gravitational acceleration. What we have is kg over the weight, okay? And this is what we defined a little bit earlier as the static deflection. So you may see that form of the equation as well in packaging application, where you have 1 over 2 pi square root of g over delta. So I know this is also should be pretty straightforward, but every year, okay, I have students that do not input that equation correctly in their calculator, they basically divide by 2 only. They don't divide by 2 pi, okay, and they get the wrong answer. So just make sure that when you plug it into your calculator, use a parenthesis for the 2 pi, okay, because every year someone do that silly mistake. Sometimes they argue with me that I made a mistake, but it's oftentimes not the case. Sometimes I'm wrong, but not in this case. So, that is the natural frequency. Good. So the next step, okay, let's kind of do a quick example that I passed around, okay, so we can apply a few concepts, okay, and try to make sense of this, and then we'll go to force vibration and try to use this to cases where I'll a little bit more apply to packaging application. So, you all have this handout. This should be right behind you. Thank you, appreciate it. Okay, so this is not a very sexy story. A mass product, okay, of 5 kilograms is placed on a cushion, which behaves as a linear spring. At rest, the cushion is deflected by 1 centimeter. Okay, pretty straightforward. So this is your example 1. So when you say at rest, the cushion is deflected by 1 centimeter, that tells you right away that this is your static deflection is 1 centimeter, so 0.01 meter. Good. Asking this, at what frequency will it vibrate if set into motion with free vibration? So, one thing you need to understand, and it's really important, if it's really vibrating, that means you're going to compress it and release it. It's going to vibrate by itself, and we assume here free vibration. That means it's going to always vibrate at its natural frequency. Okay, always, always, always. So, obviously, you can find a few things here, okay? But we know that the natural frequency is 1 over 2 pi square root of k over m, or 1 over 2 pi g over the static deflection, which is a little bit quicker to use here, okay? So, we know that the gravitational acceleration, if you use SI units, is 9.81 meter second squared. So, if it's freely vibrating, it has to vibrate at its natural frequency. So, free vibration. Natural frequency, okay, vibrations. So that means our natural frequency, if you plug in the number here, 1 over 2 pi, 9.81, divided by 0.01, you find here a value of 4.98, or basically 5 hertz, okay? And you're going to have to do some of these calculations, okay? They're pretty simple, so just make sure you understand these things. It's not, don't take it too lightly as well, because every year there's people who confuse force vibration, natural frequency, and all these things. Just make sure you get this right. If you have any question, you tell me. Stop me at any time. The second part here, I'm asking you, okay, what is the linear spring constant K of the cushion? So, we don't have much we don't have much things here. We know this, okay, static deflection equals 0.01 meter. We also have the mass, which is 5 kilograms. And we know that the static deflection, by definition, is the weight over the spring constant. So, this is mg over k. So, we're pretty good there, pretty straightforward again. So, spring constant is going to be equal to mass times gravitational acceleration divided by the static deflection. So 5 times 9.81 divided by 0.01. Plug in all these numbers, 49.05 newtons per meter. This should be straightforward. Going too fast here. Okay, last part here. It says if the mass product vibrates freely with an amplitude of 3 centimeters.
There's a question.
Yes, sorry.
What are the units for the natural frequency? Is that supposed
Hertz.
To say, oh, that says hertz.
Yeah. Hz. Thank you for this. So the mass product vibrates freely with an amplitude of 3 centimeters. So amplitude is 3 centimeters, 0.03 meters. What will be the maximum acceleration experienced by the mass product? So we don't have much equation so far to go with, okay? But one thing we assume here and we understand is that if we have a freely vibrating system, it's going to follow a sine type of vibration, okay? And we establish that the maximum acceleration, okay, is equal to the amplitude times the angular frequency squared, okay? So this angular frequency is 2 pi times the frequency. But in this case, okay, our frequency is a natural frequency. This applies in any cases. Doesn't have to be freely vibrating, okay? If it's following a sine vibration type, okay, you can always express the angular frequency by this guy here. In this case, since it's freely vibrating, it has to be expressed this way using the natural frequency. So that means here we're going to have an amplitude of 0.03 times 2 pi times 5 squared. If you calculate this, you'll find an acceleration of 29.6 meter per second squared, or about 3 Gs. Okay? And again, this equation, acceleration that links the acceleration and the amplitude and the frequency, we're going to use it over and over and over again, okay? If we have any type of movement of a product, that's going to be what links all the amplitude and the acceleration together. Okay, take your time to finish writing this. I'm going to jump to forced vibration. I'm going to have 5 minutes, so at least I'm going to introduce a few things here. Let's see. Force vibrations. So, best way I can introduce that, okay? Let's start with a schematic. Make sure we understand what's happening. So with free vibration, we compress or stretch that system and it was vibrating freely. Okay, so this guy here, okay, has a certain vibration x. So this guy here, okay, this is what we'll call the output, okay, or sometimes the response. What we have now, okay, call that. I just added it. This would be input here. This is what we call input or the drive. In this case, what we have is that the fixture where the mask is set is actually vibrating. That's what's going to generate the motion of our product. Okay? Best way to think about this, just think of a UPS truck and you have your heavy box that sits on the floor, and because of the road, you have a vibration. Okay? And that vibration moves the bottom of the box and then compresses the spring. Okay? And as a result, creates movement of your product inside the box. Okay? So that is what we're going to be dealing with and analyzing. So, let's see. I think I'm going to stop here because I have to write a bunch of definition. Okay. So, we'll continue with this Wednesday, and this will lead us to our second homework. I'm grading your homework. I'm going to return them this week and talk about them. So far, it's pretty good. And that's it. So I guess I'll see you guys Wednesday.
Is there going to be a lot of math from now on?
Yes. Which is really good, right?
Yeah, I thought it was really boring before.
And as you see, it's not. This class is more applied to anything else.
Okay, good.
A lot of the definition and